Anyhow, let's pick up where we left off with some important things, and then we'll leave you guys to do the problems and ask questions if you need to. So what we did last class is we discussed the gas laws. And if you remember, there were a few of them. So the biggest one at the end, which kind of combines them all, is this ideal gas law, which, again, this should be a formula that 15 years from now you still remember because you spent time worrying about it. Here. Although perhaps you can recite it, but you won't remember what it means. So what we have is we have an important relationship that in ideal conditions, controlled laboratory conditions, conditions on gases, temperatures, if we make things as quote unquote ideal as possible, then what we know is we know that we can quantify the behavior of gas, and the behavior sort of obeys this formula. And when I say obeys the formula, maybe I should dumb it down a little bit just to be a little more clear. You know, think of a very simple formula that if you do certain things, it obeys it. You go to the gas station and you put gas in your car. And if the gas is $3 a gallon and you put 6 gallons in, then you owe them $18. It's a simple formula. It's the number of gallons times 3. If you're driving on a highway and you average 57 miles per hour, then in 2 hours, you're going to go 114 miles. So when we say that these simple formulas determine something, this is sort of what we mean. Although the behavior of a gas is much more complicated than you averaging 57 miles an hour in your car, this formula does good in a lot of instances. It's a good predictor. It's good at quantifying, but it's not perfect. So anyhow, this is sort of the formula we ended with, and we talked about what all these numbers mean. We've said numerous times with PV, N, and TR. R is the ideal gas constant. We talked about that. Does anybody have a question? All right, so someone say something? So here's, we talk about and did we do, I don't remember if we did the example or not. Did we do an example finding the weights of gases? I don't think well, what the heck, it can't hurt, so let's do it again. So we did have a discussion though about the weights of gases. I think we talked about picking up tanks and talking about feeling how heavy it was. At a certain pressure, we could sort of predict how much was left. Okay. So here's a standard example using this formula. So we can't just use generic gas here because if we want to answer questions, we have to know a little bit about its molecular structure. So why did I write exam? What is happening? Did I stroke out again this morning? Example. All right, so let's suppose we have, let's say, 50 liters of oxygen at, say, 300 Kelvin. So if the pressure of the gas, let's say 100 atmospheres, let's determine the weight. So again, this is something you would be thinking about one day. You're like, I gotta figure out how much that gas weighs in that tank. So let's do it. Let's use what O'Grady babbled about. Okay, so what do we do? So the first thing I would encourage you guys to do, I always find it funny, when you teach sort of, well, the two of the classes I teach often, this is one of them in calculus, and and the funny thing about like a physics is like one big application of math, right? So many of us who say we don't like math, or even if we didn't mind math, one thing most humans always struggle on, and particularly in school, are these what we call word problems or story problems, and that's much of which you're doing in a physics class. Many of the problems you're solving aren't just a simple calculation at first. In order to get the simple calculation, you have to piece together the English sentences, the story, or the application, if you will. So that's kind of what we're doing here. We have to think about, all right, what are we given? And what do we want? And how can we figure out to get what we want from what we're given? And being able to do this efficiently is a skill. It requires practice and lots of it. And most of us, particularly those in classes like this, don't have that much practice. And so these things seem a lot more of a pain. And then you do a few of them, you realize that you're just plugging and chugging if you know what to plug into and then how to sort of calculate it. That being said, the way I would get you to think about this is you have a couple numerical values that are given. So we tell you that you have so many liters of oxygen. We tell you what the temperature is. We tell you that the pressure is something, and we want to determine the weight. So how do we do that? Well, we know what weight is. Weight is mass times gravity. So in order for us to answer the weight, we need to know the mass. Okay, but with oxygen, we think of it as being made up of these molecules. And so if we know the mass of 1 mole, for example, whatever that means, how can we determine the mass of the whole shebang? So let me repeat that, because maybe this was not as clear as we want. If we want weight, we need mass. And gas, unlike a solid, discussing the mass is it's similar, but it's not the same thing. I mean, if I have a phone in my hand, it's one thing to talk about the mass of that, but the mass is slightly more, not as intuitive when we say I have a canister or a tank or whatever or I guess we should use a cylinder maybe, because you're thinking of an oxygen tank. What is the mass of that gas? Well, it's going to depend on lots of things, as you would imagine, like pressure, temperature, and the volume. So here's a couple ways, or here's one way to attack this problem. So We'll use a different color. That's always fun.
It's never too late. I found this community 10 years ago when I was 32, which is a lot later than most guys, but I was still able to reinvent myself into the man you see today.
I love life and home learning.
I'd be dominating life, but for women, it is very different. You see,
the first thing we need to do is we need to first get.
They hate on women who are in solid relationships with men they love and respect. They hate on women who are still in great shape, even though they have kids. That was by the day. But here's the difference.
It should be like, we should say, whoever's TV that is, minus 100.
When a woman hits 30, it's a lot harder to stay in shape. And if she hasn't developed healthy habits like eating right and exercising, and squashed bad habits like smoking, drinking, and sleeping around, it is way too late. And if a woman cannot stay in shape, if she has bad habits and has a high body,
now it's getting louder. You do a dance. Whose computer? So who's falling asleep with the TV on? It's like an infomercial. Are you behind? I wonder who is to blame. We should minus 100. I'm just kidding. Oh my God. There was what the hell was that? A big deer just ran through my yard. All right, look. All right, back to this. That was a good little break. So the first thing I want to do is I want to get the number of moles. The reason I want to get the number of moles is because then once I have the number of moles, I can use the molecular mass of oxygen. Now you might not even remember what that is, and I'll remind you of what it is in a second. We start with PV equals nRT. Now, if we rewrite that, if we divide both sides by RT, we can rewrite it as the number of moles is PV divided by RT. So this is the number we would like to get. Now, here's the issue. We got to be very careful because we have 4 things here, which means we have 4 separate units. And if you want to do this without making a mistake, you got to make sure that your units match up. So here's how I would encourage that you think about this, particularly when you're dealing with the ideal gas law. As I mentioned on Wednesday, I think it was Wednesday, yeah. So this number R, the ideal gas constant, or the universal gas constant, I guess is more common name. If you go and look at it like on the Wikipedia page, you'll see there's like 50 of them listed, all these different units. So my advice would always be, is particularly when you're trying to learn this, is use the values of PV and T that are given, and then sort of reverse engineer which R you're going to use. So what do I mean by that? If we look at this problem, I already forget our values. I think P was, oh my Lord, P was 100. I like to use nice round numbers. So 50, 300, 100. Okay. So this is 100 atmospheres times 50 liters. Divide by, I'm going to leave R blank for now. And then this is by my Kelvin. So what was it, 300? No, what did I use for Kelvin? Oh my God, my memory is terrible. Yeah, I did use 300. So what I would do is I look at these units. I look at atmospheres, liters, and Kelvin. And so what I would do is go directly to the Wikipedia page. So I would go to Google, and I would Google gas constant. So actually, let me show you what I'm doing here, if you're concerned at all. Where's it at? Right here. So once I Google gas constant, and then I go to the Wikipedia page, I look on the right-hand side and I say, okay, which ones are going to be useful for me? Well, remember, I have atmospheres, liters, and kelvins. So I look at some of these and I'm like, okay, which ones might be the way to go? And if I look down here to this creature, I guess, can I annotate this? I think I can. I see meters cubed, which is not exactly what I want. But I do see atmospheres. I do see moles, and I do see Kelvin. So one thing I can do, you know, and by the way, how did I get to the bottom one? Well, I was just sort of looking for, so I'm looking for liters and right away, but I have a liter here and a liter here at the top, but I have pascals and bars. So at that point, I feel like I have to change, my pressure units. And then I scroll down here and I say liters, atmospheres, kelvins, and moles, but I ain't thinking straight. And because I forget that I'm in liters, and then I go down to this guy. And I'm like, well, maybe I'll use this. And then I realize, oh, I messed up. Not messed up, but I overlooked the key one. The one that I should be using, because it's set up for me already, is this one in green. So again, it might not be the most efficient way, and maybe you guys are better at this than I am. I don't know. But if I were solving this problem myself, this is how I would go about it. So anyhow, and since I'm assuming you do this all the time, that's why I ask you on your homework and on the final, what is your favorite version of the gas constant? Maybe you'll tell me why. I don't know. All right, so anyhow, the key guy here is this guy in green, because it's in liters, atmospheres, kelvins, and moles. And that's exactly what we need. And we want to make sure they all cancel out, because if you go back to our formula, which is, if I go back to our page, remember, we're calculating N. So at the end of the day, once we do this calculation, we better hope that all the units except the moles cancel out. So I'm going to be careful with how I write this down, just so we don't make any mistakes. So this is 100 atmospheres times 50 liters. So this is 0.08. What is it? 2. We'll round to 2. And if you think about the units, it's liters times atmospheres divided by moles times Kelvin. And then this is all times, what was it, 300? Yeah. So what happens is when I do, before I do any of my arithmetic, that's the easy part. The calculator will do that for us in a second. What we have to notice is that these units will in fact match up and cancel. So this might be like nightmares of like middle school or high school for some of you, but if I have these liters here, they cancel with these liters. This atmosphere and these atmospheres cancel. This Kelvin and this Kelvin cancel. And the only unit that survives is the 1 over a mole. So instead of going to the next page, let's write this down. So I'm going to kind of bury this off. So if you do the math, you get N equals, so you know, there's a lot of other tricks you could do here. That's 300, the 2 zeros goes into the 100, 2 zeros, and you know, whatever. But let's just go to a calculator and bang it out. So where'd it go? My calculator is disappearing on me. Get back here. So however you do your arithmetic, that's up to you. I'm struggling over here today. 300. So if we didn't make any mistakes, and I don't think we did. what we get is N equals 203 0.25 2. We'll round to 2. And what is this? This is moles. Now, don't forget, and this is partly going to be, maybe, I don't know if it's going to be confusing for some of you or not. Again, it's hard to gauge every one of your backgrounds in like algebra and math in general. But what I have here is I have in the denominator 1 over a mole. So in my denominator, it's 1 divided by a mole. And so you might remember from like 5th and 6th grade when you learned about fractions, when you have the numerator and you're dividing it, and in the denominator there's another fraction, what you're doing is multiplying by the reciprocal. So that 1 over the mole in the denominator technically comes upstairs. So I hope if it's not clear to you, you think about why. And if it is clear to you, I'm sorry for making you feel like I think you're not bright, but I've just seen so often that many of us just, we just don't have enough practice with this and we get confused with these units. So, great. All right, so does anybody have any questions about this calculation at all? Before we move on, does anybody think I made an error or something like that? I don't know. Comments, concerns? Okay, so what does this give us? Well, this gives us the number of moles in our volume of our 50 liters of oxygen. And so what we'd like to do now is we'd like to be able to get more information. Now that we know the number of moles, how do we compute the mass of the oxygen? So again, I don't know how everybody's background in chemistry is, but one of the things that you can do is you can Google the molecular mass of oxygen, or you can go to your periodic table. And so what I typically would tell you to do is just round it. If you look at it, it's 15.99. So let's round it up to 16. And then there's this one subtlety that maybe you know of and maybe you don't. And you might say, well, why is it 16 or why is it 32, depending on what you're looking at. Well, remember, there's some oxygen is slightly different in its structure. So we think of oxygen as O2. So a good rule of thumb is you're taking that 16 and you're doubling it, so you get to 32. So a good, I don't want to say a good, but a rule of thumb to remember is that you can either memorize the molecular mass of oxygen, which is fine. But one thing you'll notice is if you go to Google and you Google the molecular mass of oxygen, you get one answer. But if you do molecular mass of oxygen gas, you get a different number. I shouldn't say one answer. You get two different numbers depending on if you put the word gas in there or not. So anyhow, and if you're looking for the short, easy answer to this, is oxygen's usually bounded. There's a name for that. What do they call those? Like I forget exactly. I need to study my chemistry. So you got two options: learn why or just memorize. That's your call. All right, so what does that mean anyhow? So if we get the mass of one molecule, then we can multiply it by the number of moles, and then we have the total mass. That's the point. So So that's what we'll do now. So next, we get the mass. So what is the mass? Well, we have to multiply. So number of moles, and then you want to multiply by the mass of each one, if you want to think of that. So let's use M for mass. And then the number of moles we calculated to be 203.252. So that's moles. And then we multiply the mass of each one. And if, like I said, if you Google it or you look it up on the periodic table, we'll round it to 32. And that's grams per mole. And so I shouldn't be writing moles with an S. It's not correct. All right, so if you do this calculation, so 203.252 gives us what? 6504. Grams. So we've calculated, we think at least, as long as we didn't make any mistakes, which of course is possible. We're all human, we make errors. If we didn't make an error, then this is the mass of the oxygen inside our tank at a specific temperature and pressure. All right. So the last thing we would have to do then is remember that weight is defined, it's a force, it's defined by mass times gravity. So if we wanted to know the weight, we take this mass and we multiply it by gravity. So let's do that. By the way, does anybody have a question or a comment? Maybe you found an error. So here we have 6504064, and that's in grams. Now, what's our gravity? Our gravity is 9.8 meters per second squared. Now what we have to do is we have to be careful with our units here. So what are we typically using for weight? Well, here for standard humans, we typically use pounds. That's at least here in the United States. But in science, we typically use a different unit called the Newton, because Newton is the standard unit for force. So we have to decide, what do we want to write this in? Do we want to write it in newtons? Do we want to write it in pounds? I mean, I guess we can write it in whatever unit we want. So we just have to figure out what we want. All right, so what do we want to do? Well, why don't we do both, because it's good practice. The only subtlety is you might have to remember what are newtons. So, for example, what is the Newton unit? We know there's a kilogram in a meter per second squared. So right now we have this in grams. So if we want to use newtons, what we need to do is we need to write our mass in terms of kilograms instead of grams. So that's not hard to do. You can either move your decimal point down, or you can go to Google and say, what is 6504? 0.064 in kilograms. So the quick way to do this is take your decimal point and move it 3 spots left. And in which case, if you do that, and then multiply by 9.8, you get the following. Let's make sure I don't make a mistake. 9.8 times 6.504064. So if we didn't make a mistake, what we should get is 63.74 newtons, provided we didn't make an error. And then if we want, we can say, what is that in pounds? And when you do that, you're left with approximately 14.33 pounds. Again, provided we didn't make an error anywhere. So one thing you ask is this realistic? The other thing you ask is, did you make error? There's lots of places for us to make errors. We're doing lots of calculations, some in our head, some in or some on the calculator. At least I was doing it. If you do this problem, do you get the same numbers I get? If not, why? If you do, does that mean you're correct, or did you make errors, right? So there's lots of things to think about with these problems. Look, I can't make you want to learn this stuff. I mean, I know you're doing it for a class, but I mean, I can't, I pointed this out before. I can't expect that you want to look at these problems from 100 different angles the way someone like myself might. Or if you might want to do this problem and then try to think of what does this mean in the real world? I mean, that's the kind of stuff you got to do on your own time, and you'll get out of it what you put into it in that sense. So again, I know I've mentioned this a few times now. There's a few ways you can think of this type of thing. You can think of it as a silly textbook problem, or you can think of it as a way to help you practice doing certain things. Whether you think they're meaningful or useful, that's up to you. But now you know that you can do this calculation. So, does anybody have a question about this? Comment. Going once. Going twice. All right. So, excuse me. Let's move on. So we can do a little more than just this with now that we have the ideal gas law. And more importantly, if you use some, turns out not all the time, but oftentimes when we're doing science, or really, and not just regular the hard sciences, but social sciences, whatever. Oftentimes we have things that our intuition tells us should be true and they're not. But other times there's things that our intuition tells us should be true, and if it happens to be that that's the case, and that means that we get a lot of sort of nice results for free because we've already sort of did the hard part already. So an example of that, at least in my perspective, from the mathematical point of view, is what we're going to talk about now, which is called this Dalton's law of partial pressures. So one of the things that you guys are, I'm assuming, very familiar with is mixing gases. I mean, isn't that part of like the science of anesthesia? I don't know. You guys are the experts in that area, but we have to imagine that many gas mixtures are obviously made up of different gases. I mean, think of the air we breathe and what makes that. And so if we want to study the behavior of gases, we would at least hope that if a gas is made up of 3 different gases, that our knowledge of each one of those gases should be useful in understanding how the mixture behaves. So fortunately, it works out pretty intuitively. But that's not always the case. So we're sort of fortunate here that things work this way. So here's what we're talking about next. So let's suppose we have a mixture of different gases. Now, how might we get this mixture? Well, I don't know. Maybe we start with the gases separated. They all have a temperature and a pressure, and they take up a specific volume. And then under some controlled environment, we're going to combine them. So as we might expect, Mondays is the worst. The weekend of me not using this little pen or apparatus makes my penmanship get even worse. So as we might expect, total pressure. So we'll put P. The total pressure has to be equal to the sum of each pressure of the gases. So we call these the partial pressures. So we're going to write it like this: P sub 1, P sub 2, plus. And suppose we have 5 or 10, who knows? But in general, we could have n gases. So as we expect, the total pressure. So let's now write this in English so that it's a little more clear. So the total pressure is the sum of the pressure of each, I should say the sum of the pressures. Come on, pen. Don't fail me now. Of each of the gases in the mixture. So there's a name for this. It's called Dalton's law. So when we say partial pressures, what we mean is the fact that, say you have 2 or 3 gases, well, each one of those comes to the party with its own pressure. And so if we add them up, as we would, sort of expect intuitively, you add their pressures up and you get the total pressure. So another way of thinking about this is through what we call the mole fraction. So if you think about how a gas, what a gas is for that matter, And you think about, okay, if I have this mixture of gases and each gas has its own number of moles that it comes to the party with, how does this affect the total number of moles once I have a mixture? So what happens? Well, one way is to think of each one of these pressures, these partial pressures, in the following way. So what's the best way to sort of motivate this? Okay, so I don't know how chemical, I know it's not completely accurate, but one of the ways I thought about what this whole mole stuff meant is I use this weird, and it's probably a poor metaphor, but it allowed me to learn these things when I was a student, and it helps me to understand them now. You know, and now that I have kids, I see these things, and it actually makes it more clear. Like, my kids always play with Legos now, these blocks and stuff. And so I think about, like, I know gas isn't made this way, but I think about this big tower that my kid makes with all these blocks. I think of each piece as being like the mole. So there's 32 blocks. So we have, you know, 32 moles in my mixture. And then if I take all these red blocks, and I have 17 red blocks, and I have 42 blue blocks, whatever, and I combine them, then how many moles and how many blocks do I have? I don't know if that's useful, and I know it's not physically the correct way of describing it, but you need some sort of imagination on how you're going to think about how gas works. You need some sort of concrete visual on how you think it is constructed. We know, you know, we can use these words like we have moles and molecules, and they bond together, and then they bounce off. We have all that stuff, but in some sense, you need a very simplified model that you see in your head of what's happening. And I don't know if that works for you, but it works for me, at least as a student, and and even now as an instructor or as a learner, someone who always wants to learn new things. I find it useful. So there's this thing called the mole fraction. So P sub K. So let's take one of our partial pressures. What does it have to be equal to? Well, here's what we know. We know that it has to be some fraction of the total pressure, right? We know that because if we have three gases, then the sum of the three it must be bigger than each individual one. So each individual one must be some fraction of the total. So we can actually be very explicit on what that fraction is. So we'll write total here because that's what we've been writing. So we use this Greek letter. It's like an X. And what this thing is, and this is for each K. So when I say each K, well, in our generic description of this, we said we can have n different gases, n partial pressures. We have the first, the second, the third. Maybe there's 15 of them, in which case n is 15. Maybe there's 100, in which case n is 100. But it doesn't matter which one it is, whether it's the 7th or the 6th or the 39th. It's going to obey this sort of this mathematical formula. And even more importantly, we can be more specific. What is this number? Well, this is the number of moles in the kth sort of gas divided by the total number of moles in the whole mixture. Now, if you think we're just making this up, that's fine, but we're not. I mean, if you go back to the formula on the previous page, and if you think about this and you do some algebra, you're like, okay, it makes sense. Now, as I've said before, there's certain calculations and derivations we're going to do in this class. There's others that I'm just going to tell you here's a formula, and I can lead you down a path that you can derive it yourself, but we're not going to necessarily do that. How do you want to derive this thing by yourself? How do you want to sort of verify that it makes physical sense, it makes mathematical sense, and then fortunately also intuitive sense, is you just start with the ideal gas law and do some algebra. So, you know, if you start, you take, one way to think about this is you take a partial pressure. So you take your P sub 2, for example, and divide it by the total pressure. And for each one of those pressures, you write out P in terms of the other constants, in terms of the ideal gas law. And then it's literally just some algebra. And I don't, you know, for some of you, algebra is simple and easy. Others, we look at algebra like it's rocket science. And so what I would encourage you to do is to think about this. Again, what I'm telling you here is this is true. What you see on the board now, this is true. And if you don't believe me, you can derive why it's true yourself using the ideal gas law and some algebra. So that's up to you. Does anybody have a question, comment, concern? So a typical problem, and I gave you one that uses these ideas on your homework. So they're not terribly difficult, provided you know, don't make any arithmetic errors. What's nice about doing problems where you're mixing gas as well is it's really easy to check if you did things correct. You know, so for example, if you just take something simple, a basic example, I think like the one on the homework I gave you is you have nitrogen and oxygen, so you have a mixture. It's like air, right? And what you better find is that this mole fraction, so this is called, I guess I should have written this down. This is called the mole fraction. What you better find is your mole fraction of gas 1 and your mole fraction of gas 2 better add up to 1. It has to add up to the whole. So what's nice about these problems is it's very easy to see if you went around, if you did something wrong, because if you get that your partial pressures don't add up to the total, or you end up getting that your mole fraction is larger than 1, that doesn't make sense. So that means you did something wrong. Does anybody have a question, comment? Maybe you're all asleep and we don't hear the news anymore, or whatever that infomercial was. It's a good time. Going once? All right. So hopefully you guys will be able to do the problems and you won't have too much difficulty with that. Okay, so there's one more topic we want to talk about that's really important, but it's also quite a difficult one. If you think about it so far, we really haven't done, we're doing very simple things here. We're talking about how does gas behave in a closed environment. We talk about its pressure, its temperature, what happens if some of those changes, and we have the ideal gas law in the 4 basic gas laws. And then we sort of stepped our game up. We said, okay, well, as we know, there's going to be lots of gases are formed by combining other gases. And so if we want to know some things about how that gas behaves, particularly what is the mole fraction of each gas, particularly what is the total pressure if I am combining 3 gases under, you know, and I think there's definitely places where this would apply to things that you guys have likely done before and maybe in an operating room, or maybe you haven't, I don't know. But if you're administering, say, oxygen, or you're administering, actually, I gave you an example, or for the homework, we gave you a problem where we talk about we're giving gas to a patient, and this gas has a mixture, but we're pulling one type of the gas out before we give it to the patient. So, I mean, you guys, you spend time in other classes, I would assume, understanding why that's important and useful. But at least here, from the physical aspect of it and the math aspect of it, you can now quantify sort of these partial pressures, and you can quantify, not that you might want to, but you can. All right, so anyhow, the last thing we have to talk about is we have to talk about what, or how do we explain how this stuff works. Or how does this work? Now our job isn't just to quantify temperature, pressure, and stuff. It's to sort of quantify the behavior of the molecules. What are they doing? Are they moving around? If so, how are they moving around? Is there a pattern? Blah, 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 all that kind of stuff. Turns out that this is a very difficult problem to analyze. And so what we often do when things are difficult, if a question is very difficult and hard for as scientists to answer, what we do is we sort of rephrase the question, and perhaps we make it a little easier to answer. So let me give you two examples of that you probably aren't familiar with, but they, at least when I describe them, they might be. The first is, if it's a little history lesson as well, at least from physics, and since this is a physics class, I can bore you with this. So for years, physicists thought that what Newton proposed, his 3 laws, that we discussed way back in the beginning of the semester, it was believed that those things could explain everything that we see in our physical world. I mean, it makes sense. It explained the moon, it explained the planets, it explained why things fell down, it explained why we can predict if we launch a projectile at this angle, it'll land in this place. So lots and lots of things that we as humans observed were explained by Newton's 3 laws, and so we were pretty satisfied. And then in the 1900s, what they found out is once we started to be able to see really small things, like microscopic things, like atoms and stuff like that, and we started studying things like electrons, what we realized is Newton's laws weren't explaining the experiments. And so long story short, there was this new sort of type of physical theory that was developed or invented, however you want to think about it, that helped us explain things that are very small, and they help us explain things that are moving very, very fast. And so you've heard of these things before, like relativity and Einstein's sort of ideas on how the speed of light interplayed with energy. And also this thing called quantum physics, which is essentially, it starts with the idea of, if I have a nucleus and I have an electron, take a hydrogen atom, and I have this one electron that is, how do I understand that? And what we realize that we can think about it is if we tried to model it after like the planets revolving around the sun. And so Newton's laws weren't very good, and we couldn't say much about this electron. Where is it located? And how fast is it moving at any given time? And so what the question was sort of rephrased. The question didn't become where is the electron or how fast is it moving. When I say where is it, I mean with respect to the nucleus. And so that was too hard of a question to answer. In fact, impossible in many ways. And so we rephrase it and we say, what's the probability that the electron is in some distance from the nucleus? What's the probability that its energy level was blah? I don't want to get too deep in all the technicalities, but we changed the question from where is to what's the probability it's here. And one of the things we do in neuroscience is we know that we have a cell, and we know that these cells are connected And these neurons, they send signals to each other. They're chemical signals, they're electrical signals. And what we found is it's really, really hard to understand the behavior of this, say, potential difference, this voltage difference between inside and the outside of a cell. So instead of asking, what's the potential difference of a cell when this behavior happens, we rephrase the question and we say, okay, on average, how does the voltage difference change? Or how rapidly does it change? So we study those patterns. Or we might even say, what is the probability the voltage is between these two values? So those are a little easier for us to answer. Now, maybe I'm confusing you. I don't know. If I am, I'm sorry. But what I want to do is give you some sort of background on why we often change, or why we look at questions that don't seem to be the obvious question. So one of the things that's similar to the two stories I just told you is that in gases, if we want to have a theory for how gas behaves, in the sense of what is its makeup doing when we heat it or cool it? What are the molecules doing? How are they behaving? It turns out that we believe that it's a completely random process, that these molecules just behave in a very random way. And people tried to study this for years, Einstein and some other people, and they even invented new types of cool ideas, called these things called Brownian motion and what's called the Wiener process. And what one of the things that we found is that we can study these things and get more useful results if we asked about what happens on average, or what happens in probability sense. So what we're about to tell you is sort of based off of these ideas. So so maybe we start it like this. What about the kinetic theory of gas? So remember, kinetic means moving. Before, we weren't talking about anything moving, even if we understand that there's molecules moving around all the time. We were just talking about these static properties of gas, in the sense that if we have a cylinder of gas and pressure changes, what happens to temperature, all that stuff. Now we're asking, how do we quantify the behavior of the molecules that make up the gas? Okay, so here's what we know. So temperature is proportional . Oh boy, my pen is having heart failure. To average kinetic energy. So how do we write this in mathematical language? Well, turns out that what experimentation shows us is the following. So we have the kinetic energy, and what does this mean, kinetic energy? We have to be very careful what we mean. So the average kinetic energy is 3/2 Boltzmann's constant, which maybe you don't know, maybe you do. So this is Boltzmann constant, which you can Google if you're not familiar with. I would guess, I should never assume. I'm guessing you guys have at least heard it in a chemistry class before. Maybe not, I don't know. So what do we mean by average kinetic energy? Well, What we're saying is, if you could take sort of a radar gun, I don't know, it sounds like a silly way of thinking about it. So you have a gas, and a gas is made up of molecules. Let's agree that there's just molecules bouncing around in this sort of unorganized fashion. Some are moving faster than others, some are moving slow. And what we're saying is, if we, just for the sake of it, if we took 50 of these molecules, maybe we put some sort of measuring device on 50 of those molecules, and we looked at the kinetic energy of all 50, and we added them up and took an average, then that's what we mean by this. So we're averaging out, we're taking some random collection of all our molecules, we're calculating kinetic energies, and we're taking an average. So this is a pretty fascinating thing, because nowhere in this equation does it say anything about the gas that we're dealing with. It basically says that temperature is the #1 factor for how a gas is going to behave, at least its molecular structure, how its molecules will sort of be active, how will they move around. So again, where does all this come from? Well, you know, that's for another course, and the math and physics is of a much higher level. But again, we're we're trying to give you, at least with this formula right here, we're trying to give you a simplified version of a very complicated situation, at least to analyze and quantify how the molecules behave. Um, So some of you at one point, if you want to, I think the book, I know the book gives you the actual exponential function. So where does this come from? We'll write it down once. It's scary, but it maybe you know, make your lives frightening once in a while. So long ago, I would assume every one of you took a probability and statistics course. It was likely a you know, an elementary level of probability stats, but at one point I would assume, I'm guessing, because you're all, I know at La Roche, any chemistry major and biology majors have to take prob and stats. I would assume nursing, you know, you took prob and stats at some point. And what you would have talked about, if you'd have talked about distributions, like maybe you remember things like the normal distribution, like a bell curve, or maybe you might have studied things like the binomial distribution and how are statistics distributed, and we try to explain them by matching them up. So I don't know if that word is familiar with you or not, but in the study of molecular glasses, we have what's called the molecular theory of glass. Jeez, what a time to be on. We have what's called the Boltzmann distribution. Now this is a scary, and you're not going to be asked to memorize this or anything, so don't freak out. But the Boltzmann distribution says the following. So let's take n, and we're going to tell you what these things are in a second. It has this scary creature, 4 pi. You're like, why is pi involved in here? And then m, so this is, as you're going to think, is mass. And then this creature, raised to the 3/2 power. And then velocity squared. And then e raised to this creature. Remember E, we talked about this on the Faust homework when we had heart failure. So what is this? And again, don't stress over this equation other than we're going to show you what its graph looks like real quick. So this is what do you want to think about N? So there's some letters in here. We clearly know that T is temperature. Well, I don't clearly know, but that's what we used for T before. Then you have mass M. Then you have these velocities or these speeds. Now, again, this is all on an average scale. We are thinking about how a particular, okay, so on the previous page, maybe this is a better way of thinking about it. When we say the kinetic energy on average, so we're thinking about, okay, how am I getting this sample? Maybe you remember these words like sample size and population size when you were doing prob and stats. If I'm going to take the average kinetic energy of a gas molecule of a certain thing of gas, well, how do I get that? How many molecules are there? Do I just pick one and say I'm going to take you? But as you guys know, you get better statistics with more numbers. Excuse me, more sample sizes, a better way of saying it. So if I want to have a good indication of the average kinetic energy, and if I only pick 5 molecules, but there's 40,000 molecules in there, then how am I guaranteeing that I'm getting a useful sample? So again, I'm using words that you might not have heard of in a while, and maybe you haven't thought of, but I would encourage you to try to ponder this. And so if we go back to here, we can think of this as being the number of molecules. And how they are distributed. So when we talked way back in homework 1 about this exponential function, and lots of these numbers, you just for the sake of argument, just assume they're all 1 at this point. It's not exactly that important. The things that you do want to think about is, what about, notice you see something here. You see, what you'll notice hidden up here is you have mv squared over 2. What is mv squared over 2? Well, remember, that's the kinetic energy. By definition, kinetic energy is 1/2 mass times velocity squared. So we're not only here up in this exponent do you have mv squared over 2, but you also have it in some sense down here. Now, it's not precisely the same, but you do have your v squared. Excuse me. So what this formula is saying is that the number of molecules is depending on the kinetic energy. But then the kinetic energy is fighting a war here with temperature. If temperature goes up, what happens to these expressions? So this is where your number sense, and again, I know this is a very frightening equation, but if you think about the battle going on between T and the kinetic energy, and maybe battle's not a good word to use, but the interplay of how that's going to change the exponent and how that also changes what's inside the parentheses. When T is a large number, when T increases, what does that do to these fractions? So again, one of these things, if you want to have a learning moment out of this equation, then what you got to do is you got to suffer through going and looking at some graphs. If you want, I'd be happy to discuss any of this with you. But it is, looking at this is a very overwhelming. It's a very overwhelming formula. But it looks like, again, if you have your time machines on and you're going back to a statistics class and you think about these distributions, and you may have learned about the bell curve, which is the normal distribution, and then what does this look like? Well, the graph of this function is going to look very much like those bell curves. So yeah, I mean, I don't know. I don't want, I know looking at this is overwhelming, but I would encourage you to spend some time thinking about what happens if some of these variables change. What does that do to n? What does that do to the expression? And one way is to look at the graph of these functions. So does anybody have a question, concern? You're probably all sleeping now. You're probably like, I ain't looking at that thing. It's too crazy. Let me say this, though. The point, this is number of molecules. So when we call this the distribution, what we're saying is that in some sort of average sense, that the number of molecules is dependent on the kinetic energy, but the kinetic energy is dependent on the temperature. And so this equation helps you see how their interaction, when one changes, what happens to the other one. Okay, so if we believe this to be true, though, if we believe that this formula does give us useful answers, then we can steal from this. We could pick some useful things from this. And this is the last thing we're going to do today. So let's not stress too much about that scary stuff. So okay, so so what we can do is we can get info from this kinetic energy average thing. So if we recall, the kinetic energy by definition is 1/2 mv squared. So if you plug that in, now you have to be, a little careful here. So this is 1/2 mv squared has to equal 1/2. Well, what? So let me back up before I write the wrong letter down twice and then. Okay, so let me not go. I don't want to go fast because then you end up losing the thing that's important. So we start with, we have this kinetic energy on average is 3/2 Boltzmann's constant, or the Boltzmann constant, I should say, times temperature. So if I play a game, if I take the definition of kinetic energy and I plug it in there, I can get an equation that helps me solve for V. So for example, if I take this and I get 1/2 mv squared equals 3/2 kt, I can solve this. I can divide or multiply both sides by 2. That kills the fraction. So if I solve this for V, what I end up getting is I get this. I get 3 kt over m. So there's a couple things we need to point out about this. First off, what is this the velocity of? Is it the velocity of some molecule we pick out? And the answer is no. This is an average velocity because we started with a formula that was dealing with average kinetic energy. So this is sort of just like a theoretical average. This is what we expect if we randomly chose one molecule. What would we expect its velocity to be? And there's also another subtlety in this problem. I shouldn't say subtlety. So before we point that out and finish, does anybody have a question? Comments, concerns? So the question that should, well, I don't know if it should come up. Maybe you're not even pondering it. Is what we did sound? Should I have K there? Should I have Boltzmann constant? Or should I have another constant? What scale are we on? So what we're doing is we're sort of cheating right now. So one thing, and maybe I'll let you ponder this since we've already been on here almost an hour and a half. And we'll let you ponder, and then we can sort of put a ribbon on it on Wednesday. But so here's how I'd like you to think about that. Is there a flaw here? If so, why? All right. If not, what does this mean? So look, me writing formulas down and then me saying, let's solve the speed, blah, blah, blah. That is not learning. That's kind of me doing stuff and then you just writing things down. What you want to do, if you want a good learning experience, if you actually want to get something out of sitting here listening to me babble. Now maybe you don't care, and in that case, fine. I'm not mad at you. But if you want to get something from this, ask yourself, what did I do here? Does it make sense? Did I just do some algebra without by leaving out some technicalities, or what is K? I mean, I've never even told you what K is, right? Am I doing that on purpose? I don't know. I mean, I said it's Boltzmann, the Boltzmann constant, but what does that even mean? What are the units? Do units match up? If I start up here, if I start here, are the units on the left and right hand side, do they match? Do they match down here? Like, does this even make sense? And so these are things that I would ask you to think about if you want a learning experience. If you don't want a learning experience, you just take the formula for what it's worth and then do problems and then whatever. So again, it's up to you. I can't force you to try to get the learning experience. So anyhow, I hope you do, but I'm not going to be mad if you don't. Does anybody have any questions, comments, concerns? All right, if you guys don't have anything else, then I will say I'll talk to you Wednesday. I thank you guys. Hopefully you learned something today. All right, everybody. You guys have a good one. Thank you very much. Hopefully it wasn't as boring and confusing as it could have been, but I mean, you're the judge of that. So if you have any questions about homework problems and you don't want to ask them here, that's fine. Just shoot me an email. Otherwise, I got to update your grades. You guys should be fine. I'll tell you what. All right, guys. I will talk to you Wednesday. Have a great day. Thank you very much. And be safe. Take care.
Thanks.
Yep. And.